This tutorial shows how to implement wave equation in MATLAB and how to solve the PDE of the wave equation in MATLAB. So the most generalized PDE for wave equation is a second order partial derivative with respect to time and a second order partial derivative with respect to space, and c squared is the wave propagation. So let's look at it in 1D case, and we will initially set f equal to 0, but then later introduce the source. If we discretize this, we have gone through this exercise before, we can discretize this into the next time step, current time step, and the previous time step, as well as the second order derivative in space. And this term here, c delta t over delta x, is called CFL number, and this can be used to set up the ensure the stability and convergence of the scheme. And we want to make sure that this delta x over delta t, which is also called the numerical speed, is less than the wave propagation. We also want to have two boundary conditions tested. One is called reflecting boundary condition, where we set the endpoints to 0 at all times. So when the wave reaches the end, it will reflect back from both sides. The second is called merge absorbing boundary condition. So we want to make the edges so that when the wave reaches the edge, it is absorbed. And that this is called the merge boundary condition. And when we discretize it, it translates into these values for the endpoints. So this is for delta 1 and delta n. In the MATLAB code, I will be using W instead of delta because D would be awkward to use. So this is again the general code that we have used before. We set up the domain. In this case, it's 0 to 10, so with a dx of 0.1, and we want to run it for 20 seconds. I set up three variables. Wn is the current value, Wnm1 is n minus 1, and Wnp1 is n plus 1. And we will initialize these values and then later on keep marching in time. For now, I'm going to use CFL equal to 1, set the propagation speed to 1, and based on that, we can find a dt value, and it looks like it's 0.1. And this is an initial condition, so if we put this and plot this Wn, what we are doing is we're just putting a little disturbance in the middle and see what happens to this disturbance as we propagate. And we set the initial time to equal to 0. And here are the boundary conditions. As I mentioned, the values at the endpoints are 0 for it to reflect. We increment the time, we save the current value to the n minus 1, and then the n plus 1 value is saved in the n. And here is the implementation of this equation right here, with no source, of course, initially. And note that instead of using this whole thing, I'm just plugging in CFL number instead. But that's the implementation here from 2 to nx minus 1, and then we plot these values. So if we run this code, you will see it generates that disturbance propagates in both directions. When it reaches the ends, it reflects back, and it just keeps doing that. Now, if we want to change the reflecting boundary conditions to the merged boundary condition, which is the absorbing boundary condition, I have implemented that code here. So again, this is primarily this last 2 lines. I'm setting up the first point and the last point for n plus 1, and then that. So now when the disturbance or the wave reaches the endpoint, it gets absorbed. Now, one last thing I want to introduce in this is a source. So let's say we don't have any initial condition. So if we run this code, basically there's nothing. There's no disturbance, so there's no propagation. Now, if we now introduce a source here, so right here I have introduced the source at the 50th index, and all I have done is introduce a sine wave. So this is dt squared times f, which is a sine wave, right here, this part. And this sine wave is kind of using the t value, the current time value, to create this sine wave. And now we can run this code, and you can see this kind of generates a disturbance in the middle, and then it propagates. You can reduce its frequency, so this 20 is kind of a frequency I've set up, but you can set it to a smaller frequency or a larger frequency. Let's set it up to 30. Oops. And also try changing back to the reflecting boundary conditions. So instead of absorbing boundary conditions, you can have reflecting boundary conditions and see what happens. When it reaches the end, it starts to reflect back, and you can see all sorts of bizarre behavior that can happen. So this is how you can implement 1D wave equation.